Hey there, .NET devs. Today we're going to take a little bit of a side trip. We're not going to look at code at all. Instead, we're going to look at a single tool that I use occasionally that is actually really helpful. This is a signal generator, and today we're going to take a look at just an introduction to how we might use this when we're developing our software or when we're developing our applications. So first, let's turn it on. And you can see, comes up at 10 kilohertz, 5 volts with a sine wave. You can see over here on the oscilloscope, we have a sine wave. Its measurement at 10 kilohertz. And our peak to peak, it says, is 5.16 volts. So pretty close to what the output of the device here is. So the first thing we want to look at is basically we've got these functions here: frequency, amplitude, offset, duty cycle, and phase. I'm going to select frequency. You can see it's changed to yellow. And over here we've got a cursor that we can move. Now that cursor we move with these two arrow keys. So I can move it left and right. And I use the wheel to move those numbers up and down. So I can go up or down all the way to 0. I can move to the next digit over, move that up. Now if I go down, you'll see the previous number, the one just to the left of the cursor, will continue to go down. And you can see over on the oscilloscope, as I adjust these, say I have it at 7 kilohertz, you can see it's now at 7 kilohertz. So we're just adjusting the frequency of that wave. As a software developer who generally uses only digital operations, the sine wave isn't all that useful for us. So we've got a couple of options here. We can change to things like a sawtooth. If you look at the oscilloscope, I have yet to find any use for that for the work that I do. But if we change back, we have this square wave and we have what they call a pulse. The square wave is a fixed 50% duty cycle on this signal generator. I don't find it all that useful. The one that I typically use is what they call a pulse. So I select that and you can see up here it's changed to pulse. And so over on the oscilloscope, you can see that we still have a 10 kilohertz wave, about 5 volts peak to peak, but now they're nice and square. Square with these very sharp edges is what you want in a digital system. The problem that we have right now is this yellow triangle. This is our 0 voltage. So you can see we're swinging positive and negative and positive and negative. That is not terribly helpful when we're working with a system that usually runs 0 to 3.3 or 0 to 5. So what we want to do is we want to move that wave so the entire thing is above the 0 line. That's the first thing I would do. To move that, we're going to use the offset, which is this function here, and it's listed right here in this channel. So if I select offset, you can see the cursor moves here. Now, right now, half of the wave is above 0 here, and half is below. So what we want to do is we want to offset it up half of the complete range. If the complete range is 5 volts, we want to move it up 2.5. So I go over, move it up 1, 2, move it over, and then move up a half a volt. And you can see over on the oscilloscope, as I was doing that, it moved. And now the base of the wave is at the 0. And in fact, our top of our wave is off screen. So I'm going to move that down. So now our 0, again, is here, but it is at the base of the wave. And then our top is up here at 5.16 volts. That 5.1 volts is very important. When you're working with microcontrollers and embedded devices, they typically have a maximum voltage. Oftentimes it is 5, sometimes it's 3.3. It's very, very important to know the voltage range that is acceptable as an input on your device. Many devices today use 0 to 3.3 for their voltage on the bus and for their logic, but they're called 5-volt tolerant, meaning that you can give it 5 volts and it won't harm it, but it really doesn't need anything more than 3.3. The reality is logical on is usually well below 3.3 and logical off is above 0. But we're going to try to go with 0 to say 3.3. Now, 3.3 divided by 2 to give you that offset is challenging. I mean, yeah, we can use a calculator, but just off the top of my head, I find it real easy to go 0 to 4, and therefore 2 is our midpoint. And for a 5-volt tolerant system, 4 volts is definitely low enough. So what I typically do myself is I will change the amplitude. Here, this changes our overall voltage. I change it to 4 volts. Now, if you look, I still have the offset of 2.5 and 4 volts. So over on the oscilloscope, you can see the bottom of the wave has come up off of 0. So it doesn't ever come all the way down to 0 volts. What I want to do is I want to adjust that offset to 2 volts. So now we've got a complete sweep. The amplitude is 4 volts and our offset is 2. And so we're going from 0 to 4 volts here. Again, anything over 3.3, and in fact, probably anything over about 2.8 is good enough. But for my testing, I usually just go 4 and 2 because it's really easy to deal with. The next thing we want to look at is how do we adjust the frequency of this and what does that look like? I had done that before when we were looking at how we control the units. So let's go back to frequency and let's just slow this way down so that it's a lot easier to see. So I'm going to put that at 0. We're going to come over and we're going to put this at, say, 5 hertz. This is 5 pulses per second. You can see on the oscilloscope, it's having a hard time showing that just because of our scale. So I'm going to zoom out time scale. And now you can see we've got these good square waves at 5 hertz. Let's zoom in just a little bit. And I'm going to move the trigger to the left so that we can show one whole wave. An entire wave is a high plus low combination. So we've got this rising edge here. A rising edge means that the voltage goes from logic low to logic high. So we have a rising edge, then we have high, then we have a falling edge. Logic goes from high to low. And then we have a low period. That high, fall, low, rise, or rise, high, fall, low, whatever you want to look at it, that is one cycle of the wave. If I show the division, it's 20 milliseconds per division. So we've got 20, 40, 60, 80, 100 milliseconds high, and then 100 milliseconds low. So we have a 50-50 split of that duty cycle. Half of it high, half of it low. We can use the duty cycle menu here to adjust this from 50%. So if I select that, and again, we can change this. Now let's change that to 40%. You can see now we have 80 here and 120 here. This duty cycle is how much time it spends in the high state. So I can go down to 10%, and that gives us 20 milliseconds. And if I went to 5%, it should give us 10 milliseconds, right? So that allows us to adjust the amount of time that this spends high or low. Now that we understand how we use the signal generator and adjust the parameters here and what the outputs look like, let's talk about what we would use this for. Broadly speaking, I use this for generating interrupts for testing. A good example would be doing long-term sleep-wake testing, something that I'm looking at the interrupt to wake up and then go back to sleep, and I want to run it all night. I don't want to sit here and push a button. Pushing a button is another classic example. Maybe I have an application that I need to handle button clicks, and I want to see how fast can I service those button clicks. How fast can I read data coming in? There are sensors that provide pulses for data, an anemometer, so for checking the wind. Basically, those, as they spin, they give a certain number of pulses per second, equate to a certain wind speed. You can use this to simulate one of those sensors. So you can adjust this to give the edges that you want. You can adjust it for rising and falling. Let's say we wanted to do a test of a button click, effectively an interrupt, once every 5 seconds. And we want to test both falling and rising. So we have a falling edge, 5-second pause, then a rising edge. So our total wavelength is that fall plus rise. 5 plus 5 is 10. So that is our period. So the frequency is the division of that, or 1 over 10. So we could adjust this to 1/10. Now let's adjust this even further out. It takes a while for the scope to capture this data. And of course, I have the duty cycle not set at 50%. So let's come back and change that. And let it acquire the data. And you can see we have, it is low for 5 seconds, then it goes high, high for 5 seconds, then it drops back low again. Maybe you wanted to test something like a button click where it's a down, up, and then a pause of maybe, 10 seconds. Or we want to do a button click every 10 seconds. So click it, wait 10 seconds. Click it, wait 10 seconds. Again, that 10 seconds is our period. We invert that to get frequency. So same frequency, 0.1 hertz. But we would just adjust the duty cycle. Now, the duty cycle here depends on what button click does in your application. If it's you press it and it pulls high, you could then adjust your duty cycle to 0.1%. So we're going to get this very quick pulse, 1/10 of a second, so 100 milliseconds, every 10 seconds. You can see that pulse. And if I move one over, we're only getting one every 10 seconds, remember? So there you go. Oh, let me adjust that. And so we'll capture this pulse. So there we're getting a pulse that goes high one time. It is, what did I say? 10 milliseconds? Yep, 10 milliseconds long. And we get one every 10 seconds. Now, maybe your button works differently and it's always high and you press the button and it goes low. That's simply just inverting the duty cycle. So now we have a 99.9% duty cycle. Again, we're going to have one pulse every 10 seconds, and it's going to go low now for 10 milliseconds. And there you can see we have low pulse every 10 seconds. That's all I've got for today. Hopefully you found it useful. If you'd like to see more videos on tools that I use for debugging and development, go ahead and leave a comment down below. Otherwise, remember, if you've got an idea, go out and build it. Thanks for watching.